Today's video is on using first and second derivatives to sketch graphs and locate stationary points and points of inflection. In previous work back in Units 1 and 2 of Math Methods, we've already looked at stationary points and points of inflection, but we're going to look at them in a little bit more detail and specifically related to the second derivative. So the way we're going to do that is, first of all, remind ourselves that you should have already covered some work on concavity. And so concavity is simply describing the shape or the path of a function depending on the rate of change of the gradient. And there were some rules and some reminders about those things. If we have a concave up shape, then we can see that our derivative is increasing. We can see that the gradient of the curve as it passes around the curve is increasing and getting larger. And what that tells us with the second derivative is that the second derivative is greater than zero, i.e. the rate of change of the derivative is positive, it's increasing. Similarly, if we have concave down, then we have our derivative decreasing. It's going from a positive to a negative gradient, so therefore it must be decreasing. And the second derivative, the rate of change of the gradient, is less than zero. It's going towards the negative. And so what we're going to do is use those ideas plus others to help us with understanding a function. So we're going to use a pretty interesting function to do today, and that's the function you see on the screen, y equals 4x cubed minus x to the power of 4. And in order to assist me with this process, we're going to use Desmos. So I've created a Desmos graph already, and there's the function there. What I would like you to observe first of all is a couple of the key points. All right, so first of all, how many stationary points can you observe on that graph? Well, hopefully you can see that there are two. Okay, the first stationary point is here at the origin, and the second one is up here, which we would normally traditionally call that a maximum, or a local maximum to be precise, and that's at the point 327. So if we go back to here, we've got our stationary points at 0, 0 and at 327. So back to the graph, we've already identified that 327 is a local maximum, and we've got a point of inflection here. We can see that it's going from positive through gradient of 0 and then positive again. So that's a point of inflection. We're going to name that a little bit more precisely shortly, but for the moment, let's just use a term that we're comfortable with. So we've got a point of inflection, and we believe this is called a local maximum. Now, if you're not familiar with the local part of it, that'll come up again later in a different video. So just at the moment, if you're happy that it's a maximum just by looking at it, then you should be okay so far. Secondly, if we go back to the function, we can clearly see that not only is it, we have to look at the intercepts. So we've got two, 0, 0, and at 4, 0. So we'll write them on as well. So we've got 0, 0, and 4, 0. And quite obviously they're the x-intercepts, and the y-intercept, well, it's at the origin as well, so there are intercepts, plural. So what we're going to do is not only we're going to use this function, to help us explore the behavior of the first derivative and the second derivative and look at key components of those. Okay, so the first thing we're going to do is we're going to look at the first derivative. So very quickly, if that's the function, just going back to that, the function is y equals 4x cubed minus x to the 4, then what would the first derivative be equal to as a function? Hopefully very quickly worked it out. That's 12x to the 3 minus 12x squared minus 4x cubed. And if we want to continue on, we already know the symbol for the second derivative. We've covered that in previous work. D squared minus is the Leibniz form. D squared by dx squared is going to be the derivative of that, which would be 24x minus 12x squared. I won't worry about factorising or simplifying or anything like that. Okay, so let's have a look at what the behaviour of our derivative function. Let's see if we can explore a little bit of what we can see there. Okay, so pull my graph back up. So there's my original function. Let's put the derivative on. So there is the derivative function. Okay, so what do you notice? Now remember, the second function, okay, this graph here, is a graph of the gradient. So it's describing the behavior of the gradient of the original function. So as we can see, if our original function is got a positive gradient into 0 and then a positive gradient again, when we describe that, we can see that, remember, everything above the x-axis is positive gradient. Everything below the x-axis is a negative gradient. So we'll have a look at that. So first of all, at the origin, which we've already defined as a point of inflection, we can see that the gradient is positive, but it is decreasing down to 0, and then it's increasing back in the positive. And so we've got a positive gradient decreasing to 0, and then a positive gradient again. So we can see that that point there is a key value when determining what a point of inflection might look like. Okay, now the second piece of information we've got here is we can see the next time the gradient graph approaches 0. So the gradient is equal to 0 on that axis there is at the point 3, which is exactly what we determined earlier. Okay, we can see that those points line up beautifully. Okay, now there is an interesting point, and that's the point here. Okay, the point 216. That is a key piece of information. Okay, have a think for a moment. I'll stop talking for a sec. What is significant about that point? What is the gradient function telling you is happening at that point? Well, hopefully you've been able to think about the fact that that is the maximum gradient in that region. Okay, if you think about it again, the gradient function approaches the point 2, so it's getting bigger and bigger, so the gradient is getting bigger and bigger and bigger. And then at that point, it goes smaller again, back to 0. So the gradient of the original gets larger and larger and larger, and at that moment there, it heads back towards 0 again. So using, if you want to put a ruler on there and trace it along with the ruler or your hand, okay, but the gradient function illustrates that. So the point 216 is significant. So we might just make a note of that point. Okay, so the point 216 is significant. Okay. Okay, it's telling us that is where the maximum gradient in that region. Not a maximum stationary point, a maximum gradient. Okay, so it's got significant about that point there. Okay. Rightio. So let's look at the second derivative and see if we can see anything interesting about that. Okay, so there's my first derivative. I'm going to leave it on the screen, but this time I'm going to put in our second derivative. Okie dokie. Now, if we think about the second derivative is the rate of change of the gradient. So it's describing how the gradient is changing. Okay, so it's describing how the gradient is changing. So if we have a think about what's going on with our gradient function, remember, I'll turn off the original for the moment. So it's going to be, so those are the two related graphs specifically. So the lighter color, remember I'm colorblind, so red or green, whatever it is. Red, I think, might be green, whatever, this one. Okay, that one there. Okay, I think it might be red actually. That's our gradient function of the original. Okay, and we discussed earlier that it's going decreasing towards 0 and then increasing again. Okay, and that's what our rate of change is doing. It's heading towards 0 and then getting larger. Okay, so it's a negative. It's negative in terms of the gradient of that line. So the gradient of the gradient, if you like, is negative towards 0, and then it becomes positive, which is what that's showing. Okay, and then we've got a key point again. Okay, so we've got another point here, right, which is not going to, it's not significant in any way, except it seems to line up there. Okay, so that point there is significant, 112. Okay, that's an interesting point. Okay, but what's more interesting is what's going on at this point here too. Okay, now notice we discovered a little while ago what that 2 was. That was where that was the maximum gradient at that point. Okay, so the if it was a maximum gradient, then a maximum is defined as where the gradient equals 0. And that's what we see here, right, at that point there. So those are all related. So that's a really interesting point. So that point there, so the second derivative describes what is happening to the gradient function. Now, let's summarize all of that. Okay, so here we are, some graphs. Here's some information that we prepared a bit earlier. Okay, so we've got our first derivative graph, and there's our first derivative. Okay, we've identified our key significant points. We identified that 0 and 3 were stationary points. Remember, this is the first derivative graph. Okay, so 0 and 3 were our stationary points. The point 0 was was a point of inflection. Okay, we identified that the point 30 was a local maximum. So let's have a look at what the statement says. So at the point where x equals 0, the gradient changes from decreasing, positive, to increasing, positive. So the key word there is they are both positive, positive, positive. Okay, now because this is also a stationary point, but it's not a maximum and it's not a minimum, we call it a stationary point of inflection. So notice there's a new term in there, okay? And that's what we need to be able to identify. So all of the points of inflection that we've discussed up until now are a stationary point. So the stationary points were maximums, minimums, and points of inflection. So we're now going to call this a stationary point of inflection. Okay, nothing new there, just a slight change in terminology. Okay, making it a little bit more precise. The new piece of information today is this idea where x equals 2, okay, which we discussed. So that's this point here, all right, point 216. If we go back to our original function, I know this is not the exact, but you can sort of see that was this point here, okay. That was our point there. That's our point 2 where the gradient is a maximum. So remember that idea, the gradient is a maximum, not the function. Okay, so the gradient is a maximum. So we've got the gradient changing from positive to decreasing positive. So it's still positive, but it's going from increasing positive to decreasing positive. And we call that a point of inflection. Okay, so there's a difference between a point of inflection and a stationary point of inflection. And it's really important that we can tell the difference. Okay, so to summarize, here's the graph, the original graph, with our key points indicated. Okay, just to summarize. So the gradient of 4x cubed minus x to the power 4, which is what that function is, increases from 0 to 2 and then decreases. Now remember, again, we're talking about the gradient. So the gradient increases and then decreases. Okay? The point 216 is a point of maximum gradient for the interval 0 to 3. So in that particular point between the two stationary points, that's our maximum gradient. And that's a point of inflection. Okay, a point of maximum gradient. Okay, so a bit of a summary. What have we just discussed? Okay, so we're looking at the situation where concavity changes. Okay, so we've got different ways of describing concavities. Okay, so we've got points of inflection and stationary or horizontal points of inflection. The term is interchangeable. Okay, I've been calling them horizontal points of inflection, and that is actually accurate. We can call that, and why is that? Because the gradient at those points is equal to 0, as you can see here. Notice the other points of inflection, the gradient is not 0. So they're not horizontal points of inflection, but they are changes in gradient, therefore they are by definition points of inflection. Okay, so a point of inflection by definition is where the curve changes from being concave up, to concave down, or vice versa. Okay, the rate of change of the gradient is 0 at a point of inflection. That's another key piece of information. The rate of change of the gradient is 0 at a point of inflection. Okay, so we've got a summary table here. Okay, at a point of inflection, d squared y dx squared has to equal 0, and the sign changes either side. So this is what we used to do with the first derivative test. We now do with the second derivative. We look at the sign of the derivative either side, to show changes in concavity. Okay. You can also examine what's going on with the tangents. Okay. We can see that in points of inflection, the tangent at that point actually crosses the graph. That's a bit of a weird definition because tangents by definition don't cross the graph, but at points of inflection, they actually do. So that's how we use curve sketching. In the next video, we're going to look at some examples of applying the mathematics to seeing how that looks in a graph.